All right, so we're talking about redox reactions today. On screen, we have our presentation. Now we're going to be looking through, right? Let's begin by talking about some common examples of redox reaction in everyday life, right? So these are reactions that do occur very regularly. You probably may not have realized that, but when we, for example, bleach items, when we add like chlorine bleach to our clothes, or maybe when we use things like hydrogen peroxide to remove stains, the way in which the stains are removed is by the process of oxidation and reduction reactions. The colors or the dyes are oxidized into colorless compounds because the chlorate ion, which is the ClO minus ion here, actually reacts with the colored dye. And what happens here is that the chlorine ion itself is being reduced to Cl minus, right? Rusting is another example. When iron or steel comes into contact with oxygen and water, right? It is oxidized and forms what we call the hydrated iron oxide molecule, which we refer to as rust. Apples, bananas, and potatoes. You know, when we cut these fruits or vegetables and they're left exposed, they tend to form or look very brown, right? That's very common with apples. This is why sometimes when we do this and we need to prepare apples and maybe pack it in your lunch kits for you to go to school with, we will add it to some water with a little pinch of white vinegar, right? And that prevents it from happening. Preserving food is another example where chemicals like sodium sulfite, sulfur dioxide, they act as reducing agents and they stop the oxidation process and prevents spoilage. Yeah? So all of these are examples of how oxidation reduction reactions take place in very common places. Now we want to get into the more scientific reasoning and methods relating to it. So we're going to talk about what redox reactions are, what it involves. We're going to look at some examples. We're going to look at the more chemical aspect of it, right? How we could track which elements are being oxidized, which are being reduced. We briefly talked about it in our previous session on types of reactions. Now, what are redox reactions? Basically, a redox reaction are reactions when the process of oxidation and reduction, which are opposites, occur together during a chemical reaction. Now, when we talk about oxidation, we can describe oxidation as the loss of electrons. This happens when some elements in a free state lose electrons, right? And the atoms become more positive. For example, when we look at the reaction with things like sodium and chlorine coming together to form sodium chloride, sodium in its free state has the same number of electrons and protons, so its overall charge is 0. Now, when it loses its outer shell electron to form sodium chloride, it undergoes a change in oxidation state, which we'll talk about a bit later. It loses its electron, one of the electrons on the outside, and this goes to the chlorine atom, which also becomes an ion. And when it loses that outer shell electron, it becomes positive because now there's an imbalance in the number of protons and electrons. Losing electrons makes it have more protons than electrons, being overall positively charged. The chlorine, on the other hand, it's getting or gaining additional electrons, and that too creates an imbalance between the number of protons and electrons, resulting in an overall negative charge on the chlorine atom. So it becomes a chlorine ion. So basically we say, or we define oxidation as the loss of electrons and reduction as the gain of electrons. Now, this is better understood with a number of examples. So I have a couple examples listed here to show you exactly what we're talking about. If we look at, for example, the aluminum and chlorine reaction. When aluminum is heated in chlorine gas, aluminum chloride is formed, similar to the sodium chloride. The difference here, though, is that aluminum has 3 electrons on its outer shell. So it loses these 3 electrons. And when it loses these 3 electrons, we say that it is oxidized, because oxidation is loss. Loss of what? Of electrons, right? Oxidation is loss of electrons. So when it loses these electrons, we will write it in this half equation. We will refer to this as, so we would show the aluminum, which is currently a balance with same number of electrons and protons. The overall charge is 0, becoming Al3 plus because it loses the electrons, right? So this is separate from. Now chlorine at the same time gains the electrons. So chlorine is actually gaining the electrons from the aluminum. Now, chlorine could only gain 1 electron at a time, right? So what we're going to end up having here is the chlorine molecule. We're going to need 2 aluminum, and we're going to need 3 of these. And 2 aluminums mean that we're actually going to get, if we write this properly, we're actually going to end up with, I'm going to rewrite these here. 2 aluminum atoms. They give us 2 aluminum ions, each with a charge of 3 plus. And they're going to lose 6 electrons. The chlorine, on the other hand, we're going to need 3 chlorine 2 molecules. Right? And that's going to give us 6Cl minus. Right? Now, these are actually going to be getting those 6 electrons that was lost by the aluminum. It's going to be gained by these chlorine. And we'll end up with 6 chlorine ions. So the aluminum is said to be oxidized and the chlorine is said to be reduced. Yeah? So let's talk about some others. So here's another example. Reaction between magnesium and oxygen. So we have magnesium solid plus O2 gas. Now we need to balance these equations before we start to look at them, right? So we have 2 magnesium plus O2 gas to give us 2 MgO. Now the magnesium atom, they are losing 2 electrons, right? Now we're going to have 2 of them. And that's going to result in 2 magnesium ions, right? And in all, they're going to actually be losing 4 electrons. These 4 electrons is going to be given to the oxygen. And we're going to get 2 O2 minus. Each oxygen ion getting 2 electrons. So the magnesium is oxidized, the oxygen is reduced. Everybody understand that? Do you understand our equations? Everybody do understand equations? Just give me a thumbs down. Yeah, okay, no problem. So we need to keep the equations balanced, right? Now, remember when we did balancing equations? If we have magnesium plus O2 gas, and we get in magnesium oxide, which is a solid, like most oxides are solids. Here, we're not balanced. We have 1 magnesium, we have 2 oxygens, we have 1 magnesium on this side, we have 1 oxygen. So we have to balance this equation, right? If we balance in this equation, it would mean I need to put a 2 in front of here, changing this to a 2. And then I'll need to put a 2 in front of here, and that changes this to 2 and this to 2 as well. Now I'll be balanced because I have 2 Mg's on this side, 2 O's on this side. You okay with that part? Good. Now, when we're talking about you're looking at either side of the equation. Here, magnesium is in its elemental form, meaning that's just a magnesium atom. So its oxidation number, its state, its charge is 0 because we have the same number of electrons and protons. On this side, when it bonds ionically with oxygen, it becomes Mg2 plus, right? Now that suggests that it lost electrons, right? Now, what is actually happening is this magnesium on this side is going to magnesium 2 plus, but it's losing electrons. It is losing, we have 2 magnesium atoms here and 2 of them here, and each of them are giving up 2 electrons. It means that we have 4 electrons that is no longer with the magnesium atom. So this magnesium, 2 magnesium atoms, is becoming 2 magnesium ions and is giving up, or it's losing 4 electrons. Now these electrons are not just floating around in space. It is being accepted by the oxygen. The O2 molecule, right, which in this state is bonded covalently together, so there's a balance in the number of protons and electrons, is going to accept these 4 electrons. And when it accepts these 4 electrons, remember there are 2 of them, you're going to get 2 oxygen molecules, and each of them are getting 2 additional electrons. So that's going to create an imbalance between the number of protons and electrons. And each oxygen atom, or ion in this case, is going to have 2 more electrons than protons, giving it a charge of -2. Everybody understand that? You any good with that? Rihanna, you alright with that? Gabriella? Rihanna, we're good with that? Antilia, Angel? Yes, everybody alright with that? Okay. Let's look at another example, right? So we're talking about redox reactions. Just to recap, we said that redox reactions are where oxidation and reduction, which are opposite processes, occur together in certain chemical reactions. Oxidation, we're describing it as the loss of electrons. This involves an atom becoming more positive. So when it loses electrons, you have more protons than electrons, giving it an overall positive charge. And then reduction is where we gain electrons. If we gain electrons, the atom becomes more negative because it has more electrons than protons, right? So we're looking at another example, the reaction between hydrogen and chloride. Now, hydrogen in its elemental state or in its molecular state is H2 gas. So too is chlorine, right? So hydrogen, we look at hydrogen. H2 is really 2 molecules joined like this. They share an electrons to complete the outer shell. So it's balanced. The overall charge is 0. Now, if they each split up and they lose the electron that was on the outer shell, they lose it like this, then it becomes a H plus ion. But remember, there were 2 of them. So it's losing 2 electrons, right? And we're going to have the H2 splitting up to give us 2 H plus ions. These are cations here, positively charged, with its 2 electrons, right? This is how it's going to combine with chlorine in order to make HCl. So these here are what we call half equations. We're looking at the pieces that is putting together the HCl. The H2 alone is splitting up from H2 to give me 2 H plus ions with 2 loose electrons now that could be donated to the chlorine this Cl2 gas here is going to accept 2 electrons and become 2 chlorine ions. Everybody understand that part with the equation? So because the hydrogen is losing electrons here, right? Don't mind it's saying positive. Remember, it's losing it. It's no longer with it. And here, the chlorine is gaining electrons. This is oxidation, loss, oil rig, and this is reduction. So we say the hydrogen is oxidized and the chlorine is reduced. So whichever element loses electron is the one that is oxidized, and whichever gains electron is the one that is reduced. Does everybody understand that?
Yes.
Yeah. So in all of these reactions, this is another reaction. This is what we call a displacement reaction. We talked about displacement reactions last week. Anybody know what's a displacement reaction? Okay, tell me.
No, sir.
Forget this. So this is when metals, right, or sometimes non-metals, displace or replaces another metal that is lower in the reactivity series. So we saw this reaction last week. This is a single displacement reaction because zinc is replacing copper. Zinc is more reactive than copper. So in a solution, the zinc solid will kick out the copper and form zinc sulfate. And the copper will precipitate out and become copper solid. Right? So when this happens to, on this side of the reaction, zinc here in its elemental form, this is just zinc alone. It's not reacting with, it's not combining, bonding with anything else. So in its elemental form, it has balanced number of electrons and protons. So its overall charge, or what we're referring to as the oxidation number, is 0. Right? Because there are equal number of electrons and protons. Give me a thumbs up if you understand that. In its elemental state, the overall charge, or in this case, we're not talking charges so much, but oxidation numbers, but they're used interchangeably, right? It's 0 because you have the same number of electrons and protons. Now, when it kicks the copper out to combine or bond with the sulfate, the zinc here becomes zinc 2+, right? It becomes zinc 2+ because it is giving up 2 electrons to sulfate. Sulfate is actually taking those 2 electrons, and this is why they could bond together. So what is happening is we have the zinc, and it is going to zinc 2+, and it is giving up 2 electrons, right? Now, while that is happening, sulfate on both sides of the equation is still 2-. Nothing is happening to the sulfate. But copper, on the other hand, which was 2+ here, now goes to be copper 0 on this side. So copper is actually accepting those 2 electrons that zinc threw out. And when it takes those 2 electrons, it goes back to being copper solid, which has an overall oxidation number of 0. So 1 lost electrons and 1 gained electrons. The loss of electrons is referred to as oxidation, and the gaining of electrons is referred to as reduction. Everybody understand that? Another thumbs up if you're okay with that. Look at this one. Same thing again. Iron and copper 2 sulfate. The iron is going to displace copper from its solution, right? Because iron is more reactive than copper. When it does that, the ion is going to lose 2 electrons and be oxidized. Oxidation is loss. Copper is going to gain those same 2 electrons that was lost by the ion, and it's going to become copper 0, right? So the ion is oxidized and the copper is reduced. Let's look at example 5. Reaction of chlorine with potassium iodine, sorry. Chlorine 2 and potassium iodine. The chlorine is going to displace the iodine. Again, this is a displacement reaction where the more reactive halide, if you remember from last week's session, would displace one that is least reactive. So the higher they are in group 7, the easier they will displace or kick out one that is lower. Chlorine is second from the top. Iodine is 1, 2, almost third from the top. So chlorine will kick out the iodine and bond ionically with the potassium. So it goes from being C2, 0, it gains 2 electrons and becomes Cl minus, so reduction has taken place. Iodine, on the other hand, was initially I minus, and it is losing the 2 outer shell electrons, or the 2 electrons that it had, in order to become I2. It's going back to 0. So the iodine ions are oxidized. The chlorine molecules are reduced. Yeah, everybody okay now? Here's another reaction. Aluminum oxide. All right, I want to give you a couple to try on your own. The aluminum is losing 3 electrons to become Al3+, and there's 2 of them here. Right? And the oxygen is gaining the electrons to be reduced. Reaction in a hydrogen fuel cell. Hydrogen to make water, H2O. Here the hydrogen is in its elemental state. 0 is its overall charge. And then when it combines with oxygen, we will go from being H2, which is 0, to H+. It is losing 2 electrons. These 2 electrons are gained, right, by the oxygen to give us H2O. So hydrogen acts as a fuel, a reducing agent, and oxygen is acting as something called a oxidizing agent. We'll talk about that shortly. Here's another one. Just 2 more. Copper oxide and hydrogen gas. Look at what is happening. You have to look at the oxidation numbers. The oxidation numbers are to the top, right? And it is what helps to create the formula, right? Now, this is why when we did the cations and anions, and I asked you guys to learn the common cations and anions, this is where you're getting those charges from, right? So copper here has a charge or oxidation number of 2+. Why? Because it loses 2 electrons. Oxygen has a charge of 2- because it is gaining 2 electrons. Now, when we look on the opposite side of the equation, the copper went from being 2+ to being 0. Sorry, to being copper 0, because it is gaining electrons. It is gaining back its electrons to have balanced number of electrons and protons. So if it gains electrons, it is reduced. On the other hand, the hydrogen, which originally was 0, here it becomes plus. So it's actually losing electrons now. So we say that it is oxidized. Last example before we try some questions. Reaction between iron trioxide and carbon. Now, iron trioxide, when you see these things in this compound state, it means that you have charges on top of here. But when you see it in its free state by itself, not combined with anything, it has a balanced number of electrons and protons. So its overall oxidation number is 0. Now, you need to compare the same ion on both sides of the equation. So, for instance, if I look at iron here and iron here is balanced. It's iron solid. It's not combined with anything else. On this side, this is actually 3+. Now, to go from 3+ to 0, right now at 3+, it has more protons than electrons. So to go from 3+ to 0, it had to gain 3 electrons so that the charges, the overall oxidation state would have increased, or the number of electrons and protons would have been the same. So we say if it's gaining, reduction is gain, ion was reduced. And you see, with these reactions, redox reactions, if one is being reduced, then something else is being oxidized. So the carbon, which is currently at 0, is changing here to a 2 minus state. It is losing electrons to go from 0 to become, not 2 minus, sorry, to become 2 plus. Right? So we say that the carbon is oxidized. Everybody okay with that? All right, so if I'm given a question such as this, identify which of the following redox reactions and say what is oxidized and what is reduced. Now, to begin with, what I was saying is that to determine if something is a redox reaction, based on what we looked at in the note, redox reactions are where both oxidation and reduction occurs, right? You have both reduction and oxidation occur. Now, oxidation is the loss of electrons, where an element in its free state or compound loses electrons and then becomes a charged particle, right? Reduction is when an element in its free state gains electrons and become a charged particle, right? An ion, in other words. So we're looking at these equations, and we're looking where things going from having a charge, or what we refer to as an oxidation number of 0. Elements in its free state, like calcium here, this is in its elemental state. Calcium, which has a remember, we did the electronic configuration of calcium 2882. This means that calcium has 2 electrons on its outer shell. Inside of its nucleus, you have 20 protons, 20 neutrons. Right? I'm just going to draw the outer shell, right? The outer shell has 2 electrons. If calcium loses these 2 electrons, then on the outer shell now, you will only have 18 electrons remaining on the outer shell, meaning that you will have 2 more protons than electrons, causing it to become calcium 2 plus. Is everybody fine with that? Everybody understands that? That is the change that we're talking about. If we have calcium with the same number of, I'm going to draw the other shells. That's why I say everything linked together. So in the nucleus, you have 20 protons, 20 neutrons. This is the calcium atom here, right? First shell have 2 electrons. Second shell have 8. Third shell have another 8. Fourth shell have 2. So this is calcium. Now if calcium loses its outer shell electrons, so now trying calcium with a completely filled outer shell, because you're going to lose that outer shell with the 2 on it. What is happening to the calcium here now is that Because you have 20 protons which are positive and only 18 electrons now. Because now we're going to get calcium that is you have 20 protons, but you only have 18 electrons. So you're going to end up with a +2 charge. And these 2 electrons going to be on the outside. Understand that? It is changing. It is going from this, which is on this side here with the same number of protons and electrons. So the overall charge or the overall, I don't want to use the word charge. The correct word is oxidation number, right? But the overall oxidation number is 0 because you have the same number of protons and electrons. When it reacts with the chlorine and we get on this side of the equation, it changes from being calcium in its elemental form to a calcium cation. It's a positively charged ion because it lost 2 of its electrons. These are the 2 electrons that it lost here. Understand now? So we're going from Ca0 to Ca2 plus. How did that happen? It happened because it lost electrons. Oxidation is loss. Loss of what? Electrons. So if calcium went from 0 to calcium 2 plus with 2 electrons hanging around here, this is what we refer to as oxidation. Now, while that is happening, chlorine, on the other hand, is going from 0 to 2 minus, not 2 plus. Chlorine is actually gaining 2 of these chlorine molecules, ions, sorry, is gaining the 2 electrons that was lost by calcium. So the Cl2 is gaining 2 electrons and it is forming 2 chlorine ions. Right? This is actually a single minus here, but you have 2 of them. Does everybody understand that now? So chlorine is being reduced, or reduction is occurring for the chlorine. Reduction is gain of electrons. It's gaining electrons. That's why it has a negative charge. So when it loses, it's positively charged. When it gains, it's going to be negatively charged. So we could say that this here is oxidized, while this here is reduced. So this entire reaction is a redox reaction. E is a redox reaction. Is everybody okay with that? Now, you don't have to draw these diagrams, right? I drew these diagrams so you'll understand that change in oxidation state is happening because electrons are being lost and there's an imbalance between the number of protons and electrons, accounting for that change in oxidation number. Because all of this has to do with losing or gaining electrons. The loss of electrons causes the oxidation state to increase. It is going from 0 to +2. The gaining of electrons causes the oxidation number to decrease, going from 0 to negative. Everybody follow that? Aaron, we good with that? Everybody understand? Good. So using that same example that I just did, I want you to compare on either side of these equations. This is a comparison. You are comparing the Cl2 molecule with the Cl ion here. You are comparing the hydrogen with this here. Is the hydrogen remain the same? You are comparing the sulfur with sulfur here. Now, in some instances, some of them won't change. For example, the hydrogen here. This hydrogen is bonding with sulfur, is bonding with chlorine here. There's no real change. This is still plus and this is still plus here. But sulfur, on the other hand, is going from being a -2 to being a 0 on this side. Right? How can I tell? I could tell based on these formulae, remember to create or write these formulae, we had to pay attention to the change in the oxidation numbers, right? For this to be H2S, it meant that H is positive 1, S is 2 minus. So you need 2 of these H's to bond with one of these S so that the overall charge on the molecule is 0. Yeah? So tell me in part B, what is being oxidized? What is being reduced? Do you try that for me, part B? All right. So we want to identify is it a redox reaction? We want to also identify what or who is oxidized and who is reduced. Let us begin by looking at on either side the elements, molecules, or ions. Here we have chlorine, we have H and sulfur. Then we're going to talk about the oxidation number on this side. So here the oxidation number is 0 because it's a molecule, right? Here, this is going to be +1 because H2S is not an elemental or free state. This is what we call a compound, an ionic compound. So from these reactions, your ability to identify what are molecules, compounds, and atoms or elements is important. Sulfur by itself here is an element in its free state. This is an atom, right, of sulfur. HCl is an ionic compound. And this here is a molecule. The ionic compounds involve what we know about ionic bonding, electron transfer. And when that happens, it results in the formation of ions. So it means that they're going to have changes in their state in terms of their oxidation numbers. Here, the sulfur is a -2. If we go back to our chart, right? Sulfur is, when it's bonding with something else, it's going to be a -2. On this side, we're doing the same thing. We have H, we have Cl, and we have S. H in this case is still a +1. Cl is a -1, and sulfur is a 0. So let's compare them. Let's write them in the same order so it's easy to compare. Cl here, the oxidation number is going to -1. H here, same +1. Sulfur here, 0. Right? Now let's talk about them in terms of electron gain, electron loss. Let's talk with chlorine so far. So here, on this side, chlorine is 0. But then it goes to -1. What will cause it to go to -1? Would that change in oxidation number be a result of a gain in electrons or a loss in electrons? What we need to relate this to is what happens when we gain electrons. If we gain electrons, there are more electrons than protons. I'll write it with, so I'm not confused. Protons are positive, right? So that would result in a overall negative charge or negative oxidation number, right? In other words, if we are on a number line and we're going from 0 to -1, that is a decrease in oxidation state or number. If I lose electrons, then I have less electrons than protons. So it becomes more positive. If it becomes more positive, that means I'll go this way on the number line. So that'll be an increase in oxidation number. Agreed? So let's think about these changes in oxidation numbers. 0 to -1, and I'm going to put them on either side, right? 1, this is your number line here, 2, -2. If I am at 0 and I go this way to -1, would you consider that a decrease or increase? Anybody? 0,
Yes.
a decrease because we're going back down, right, to -1. So this was a decrease in oxidation number. A decrease in oxidation number is a result of a gain in electrons. And remember we said oxidation is loss of electrons. Reduction is gain of electrons. So this means that here, this was a what? This whole thing here was reduced. Give me a thumbs up if you agree with that. See how we reasoning it out? Look at this one. H. H is +1 on this side. That's why I have to have 2 of them because the S is -2. And H is +1 on this side because the Cl is -1. Right? So did H change? No change. Agreed? Right. Sulfur now. On this side, sulfur is -2 because it is bonding ionically. And the key thing here is to look at these ionic compounds because they are where, this is where we're going to see, you know, those changes in states. It is -2 here, but then it goes to 0 here. So if I'm at -2 and I go to 0, is that an increase or decrease?
Increase.
Increase. It is an increase. And we say an increase is synonymous with a loss in electrons. And loss in electrons refer to oxidation. So the sulfur was oxidized. So let's make a little table. Oxidation is loss of electrons, right? Everybody agree with that? When they lose electrons, we have an increase in oxidation number. Agreed? So we could identify an increase in oxidation number being a result of a loss of electrons, and that would imply that oxidation occurred. And that particular element was oxidized. Yeah? More thumbs up if you agree with that. So then the opposite happens to reduction. We have a gain of electrons. This results in a decrease in the oxidation number. And we could say that that particular thing was reduced. Does that make sense to everybody? Yeah? So back to our handout. So the oxidation number, based on what we were just talking about, shows the number of electrons lost or gained or shared during a bond formation. It can be positive, negative, or zero, right? So we saw that chlorine, for example, had an oxidation number of 0. Whereas in our last example, hydrogen had an oxidation number of +1, and that remained the same on both sides of the equation. Chlorine had an oxidation number of 0, and then it became negative. Now, in order to work out unknown oxidation number, there's some rules that you need to know. The oxidation number of an atom in its elemental form is always 0. And you'd have picked up on that already from our discussions. So H2, O2, Cl2, Na, Fe, sulfur. Once it by itself, molecules or elements, the overall oxidation number is 0. Yeah? The sum of the oxidation number in a compound, whether it's ionic compound or covalent compound, the sum of all of them, when we add up all of the oxidation numbers, we will get 0. So for example, in H2O, we know the H is a +1, and you have 2 of them. The oxygen will have to be 2-, so that when you add +2 and -2, the overall oxidation number is 0. Everybody okay with that? Yeah? Good. Anybody not okay with that part? We good? Right. Now, in some polyatomic ions, the overall charge is not 0. So for example, the sulfate ion, SO4-, has a charge of 2-. The overall oxidation number, SO4, is 2-. So if I need to work out what the oxidation state of sulfur is in SO4 2-, we will need to do a little bit of algebra, in the sense that we know that oxygen has a charge of -2, and there's 4 of them. So 4 by -2 is going to give more what? -8. Now the overall charge of this entire polyatomic ion is -2. It is not 0. So if I want to find out what sulfur is, then I have to move this -8 across here, just like in algebra. And what we will get is 8, because it's -8 here, become +8, -2. So sulfur is actually +6 in this polyatomic ion. Now, there's some other common oxidation numbers that you have to remember. For example, hydrogen is always +1, except in the case of a metal hydride. So if we put something together like magnesium hydride like this, The H here is not positive because the magnesium is the one that is positive. The H becomes a -1 instead. Understand? Potassium hydride. Same thing. It will be KH. The H will be -1. Oxygen is always -2, except in the case of a peroxide, where oxygen will be -1. All of our group 7 elements, chlorine, bromine, and iodine, are -1 all the time, unless they are bonded to oxygen or fluorine. Our group 1 metals all have a charge of +1 because they have 1 electron on the outer shell to lose. Our alkaline earth metals, which are group 2 metals, has a +2 charge. Now, we could use algebra to find the unknown. Now, we always write an equation to the total charge being 0 for compounds, or if it's an ionic compound, we write it to the charge of the ion. For example, this is the chromate ion. If you look at the table that I told you guys to learn, the common anions, you'll see the chromate ion. The overall charge on this is -2, right? Now, if I want to work out the oxidation number of chromium, because we know the oxidation number of oxygen, or oxide in this case, is -2, we will write a simple equation where we will represent the chromium ion as X. Now, there's 2 of them, so we'll have to put 2X. There's 7 O's, and O's carry a -2 oxidation number. The overall oxidation number on this polyatomic ion is -2. So we will put it equal to the charge of the ion, not 0. And then we will solve for X. So we'll get, well, as you can see here, 14 is equal to -2. 2X is equal to 14 minus 2. So 2X is equal to 12. X would be equal to 12 over 2. X would be equal to 6. So the oxidation number for chromium is +6. Everybody understand that? Right? Here are some more examples. If we want to find the oxidation number of sulfur in H2SO3 hydrogen sulfite, we know that H has to be +1. That's what the rule said. Only unless it is in a metal hydride. This is not a metal hydride, so H is +1. We know O has to be -2. Now there are 3 O's and 2 H's, so we will have 2 by +1, 3 by -2. The overall charge oxidation number on this is 0, so we put it equal to 0. So X, we let in SVX, is what we're solving for. 2 by 1 will give us 2. 3 by -2 will give us -6. 2 from -6 will give us -4. I carry it across the equal sign. It means that sulfur has an oxidation number of +4. Look at this one. This is the nitrite ion. Oxygen we know to be -2. We're going to put an X for nitrogen because we want to find out that the total charge is -1. So we're putting it equal to -1. 3 by -2 will give me -6. I carry the -6 across my equal sign. I'll get -1 plus 6. And that will give me +5. So the oxidation number of nitrogen in this nitrate 5 ion is +5. I think I said the wrong thing just. Manganese. We want to find out manganese, which is Mn inside of the potassium manganate 7. Right? K is +1 because that's a group 1 metal. O is -2. We know that. Mn will put as X. So we have 1 plus X plus 4 O's. So 4 by -2. 1 minus 8 will give us -7. We carry it across. We get X to be +7. Everybody get the hang of it? All right. I want you to try some for me using the rules that we just talked about. And these 4 questions here, I want you guys to work out using algebra the oxidation number of the underlying element. Right? Try that so. Let's take a look at the answers. Now, we have sodium sulfate. We want to find the oxidation number of S. Now, the sum in our compound, the sum of the oxidation numbers would be 0. So, Na is going to be +1 for each of them. So, the total is 2 plus. O is going to be -2 for each one. So, the total will be 4 by -2, which is -8. And we will let S be equal to X. So, what we would have is an equation that looks like this. The 2 sodiums by +1 plus X to represent the S. 4 oxygens at -2. So 2 by 1 will give us 2. 4 by -2 will give us -8. And then we solve in for X. So 2 minus 8 will give us X minus 6. Carry the 6 across and we'll get X to be +6. So S in sodium sulfate has an oxidation number of +6. All right? Now, if we react sodium sulfate with something else, and the S changes from a +6 to +4, then we would say that S was reduced because we had what? A decrease in oxidation number. And based on what we talked about earlier with our little table, a decrease in oxidation number suggests reduction has occurred. Right? Because it means that you would have gained electrons, causing the imbalance between the protons and electrons to drop. Right? Now let's talk about ammonium. This is the ammonium ion. We want to find the oxidation number of nitrogen. Now hydrogen we know is always +1, right? Except in the case of metal hydrides. Now we have 4 hydrogens, so that's going to be 4 by 1, which will give us 4. So X plus 4, here the overall charge is not 0. The overall charge here is actually +1. So that's an important thing that we need to take consideration, because that's what we're going to put it equal to. So X plus 4 is equal to 1. We carry the 4 across. It means that X is going to be -3. So N has an oxidation number of -3. If we react the ammonium with something else, forming N2 gas, it means that the N will go from -3 to 0, which represents an increase in oxidation number. The increase in oxidation number meant that it lost electrons to become more positive. So we would say that nitrogen would have been oxidized. The other one is CO3 2-. We want to find C. Now the total charge on the ion, this is not a compound or molecule or atom, this is an ion, is -2. We know O to be negative, oxygen to be -2, and we have 3 of them. So 3 by -2 will give us -6. We carry -6 across. -2 plus 6 will give us +4. So carbon has a +4 charge, a +4 oxidation state. This is potassium dichromate, and we want to find chromium. Now, the total compound is 0. Right? Oh, I think I'm missing something. No, it's 0. Sum of the entire thing is 0. Right? Chromium. Potassium dichromate, sorry. Now, potassium is a group 1 metal, so we know that is going to be 1. Oxygen is -2. Right? So the total of that 7 by -2 is -14. We have 2 potassium, so 2 by 1 plus 7 by -2. We get 2 plus 2x minus 14. That's going to give us -12. Carry the -12 across, it becomes positive. We divide by 2. It means our chromium has an oxidation number of +6. Now, when you're doing these types of questions to identify the oxidation number, you want to write down the known oxidation numbers first. You always write the algebraic equation showing the sum of the oxidation numbers if it's 0 or the overall charge. You're going to solve for the unknown, and then you're going to state the oxidation number with the sign first, right? Now, in some instances, if you're given a reaction and you could look at the change in the oxidation state, you'd be able to say whether it was oxidized or reduced. Remember, an increase in the oxidation number, right? An increase in the oxidation number would suggest what? That you lost more electrons or gain more electrons. If I went from 0 to +2, that's an increase, right? That would mean that I lost electrons. So that means it was oxidized. If I went from +2 to -1, that would suggest a decrease. That means I'm gaining more electrons. Understand how to think about it? So I was reduced. Everybody okay with that? So in terms of oxidation numbers, anytime our oxidation number increases, that means oxidation happened. Anytime our oxidation number decreases, that meant that reduction occurred. Is everybody all right with that? All right. So we're going to do a little bit of practice with solving for oxidation numbers. Let's switch our screens. Sorry. Any next question? Let me just repeat myself for this one here. Sorry about that. We're going across. X, we don't know what chromium is. We have 4 oxygen, so 4 by -2. And the overall sum of the oxidation states is -2. 4 by -2, we give them a -8 here. And then I'm moving this across, make equal sign. So I'm going to get x is equal to 8 minus 2. Right? 8 minus 2 will give more 6. Right? Next question. We have Na is 1. There's 2 of them. So I get 2 by 1. S we're trying to find. We have 3 oxygen. So 3 by -2 will give me a -6. Right? So 2 plus x minus 6. We're working out the 2 and the -6 to give more x minus 4 is equal to 0. And then we're moving that -4 across. We're going to get x is equal to 4. This one, we replacing the C with an x, but there's 2 of them. So we're going to have 2x. There's 4 O's, so we're going to get 4 by -2. The overall sum of the oxidation numbers or the overall charge on the ion is -2. So we're putting it equal to -2. Next, we're going to work out this part here. We're going to get -8. Then we're going to take this and move it across the equal sign. So we get 2x is equal to 8 minus 2. 8 minus 2 is going to give us 6. And then 2 divided, or 6 divided by 2 rather, will give us 3. So in this case, this is our +3. We said this is our +4 here. Next one, we have the Mn2O7. Right? We're representing the Mn with an x, but there are 2 of them, so we have to put 2x. There's 7 O's, so 7 by -2. The overall charge on this one, it's a ionic compound, and its overall charge is 0, so I set it equal to 0. Working out this part next, 7 by -2, we give a -14. Moving the -14 across, we're going to get +14. Dividing 14 by 2, going to give us 7. So here this is going to give us +7. Right? Next one. X to replace the V. 2 O's. The overall charge is +1, so you have to put it equal to +1. Next, we're working out 2 by -2. That'll give us -4. Move that across. 1 plus 4 will give us 5. Hydrogen will be +1. Oxygen is -2. There are 3 hydrogens though. So we have to do 3 by +1, 3 by -2. We representing the p with a x. The overall charges are 0. We will then work out 3 minus 6. That'll give us -3. Move the -3 across the equal sign. We're going to get x is equal to +3. So this is our +3. ClO3, 4 minus. The overall charge on the ion is -4, so you're setting it equal to that. Oxygen we know to be -2, but there's 3 of them. We're working out that. Again, -6. We move that across. You get 6 minus 4. X is equal to +2. So the chlorine has a +2 charge. This last one, the overall charge on the ion is a +1. For plus by itself, that's 1. 4 H's, so that's 4 by 1. Give us 4. Carry that across, you get 1 minus 4. X will be equal to -3. So the N, has a -3 charge. All right? Okay, so we covered a bit on redox reactions. We still have a few more things to do on it, but we're gonna put a pin in it there for today. Next week we'll continue. I'd like you to read over what we did on the handout, right? Read over, look at your rules, make sure you understand what is happening that causes the changes in oxidation states and how that relates to loss or gain in electrons or increase and decrease in oxidation numbers. That's the key to understand redox reactions, right? We'd also look at some more reactions next day where we could look on either side of the equation to determine what oxidation states are changing. So that way you'd be able to tell what is being reduced, what is being oxidized. We'll also introduce the terms oxidizing agent and reducing agent as well. All right? So until next class, that's it, guys. Thanks for tuning in.
Okay, Professor.